All right, next thing, lesson 4, wind patterns. Told you I was going to go fast today. Okay, I'm going to try and get through. I won't get through all of this one, but I'll try. Okay, all right. So yeah, I don't know. I just love the Far Side. I don't know if anyone else reads the Far Side, but it's funny how the inside of that fishbowl ever caught on fire. I'll never understand, but yeah. Okay, so what we want to get out of today is understand how energy is distributed on Earth. So we just finished talking about the mechanics of that, okay? Convection. Well, now we're going to look at convection specifically as wind and all the wind mechanisms that are present on Earth that help to move around the sensible heat and the latent heat that is present on Earth. Okay, understand the role winds play in distributing energy. Know what the Coriolis effect is, okay, and how that distributes energy. Anyone ever heard of this, the Coriolis effect, before? Okay, and then recognize that global wind patterns are a product of convection as well as the Earth's rotation. Okay, the fact that the Earth rotates actually plays a role in winds. All right. Planets like Venus, for example, that rotate extremely slowly. In fact, Venus rotates so slowly that a day on Venus is longer than a year on Venus. Okay, like a year on Venus is like 225 days, okay, Earth days, and 1 day on Venus is like 235 Earth days. Okay? It actually spins that slow. Right? What that means is there isn't anything that's causing rotation within the atmosphere as well. Now, the atmosphere and the solid part of the Earth are semi-connected. They're not fully connected. Okay, so the Earth can spin, and it can spin under its own atmosphere. Most of the time they go together, but sometimes they don't. Okay, so we get this feeling of if you stick your head out the window of a moving car. Not that you should do that, but okay, if you stick your head out the window, okay, it feels what? It feels windy, except that it's not. It's that you're moving through the air at a high rate of speed. Well, that's kind of part of what causes wind on Earth, is the fact that the Earth can spin underneath its atmosphere because its atmosphere is fluid, but the surface of the Earth is solid. All right, so the Earth's atmosphere is always moving, okay? Not because the Earth is spinning, but because there's differences in temperature and differences in pressure. That's what gets the atmosphere moving, okay? But it also has to reflect that the Earth is spinning under it, right? So if I'm standing on the Earth's surface, okay, the Earth spins this way, all right? So the sun, we'll say, is out here, right? That's why the sun rises in the east and sets in the west, okay? So, well, let's say the sun is over here. It'd be easier to diagram that, okay? So if the sun is over here, as the Earth is spinning, okay, and it comes into view, I'm going to be seeing it in the east, and then the Earth is going to rotate under the sun. I'm going to see it set in the west. Everybody all right with that? Okay? All right. As that's happening, okay, if the atmosphere just happens to be, let's say, oddly, perfectly still that day, the Earth would spin under it. And I would feel as though it was windy because I'm being pushed through the air, and the air is sitting still. Okay, so that appears to do something called the Coriolis effect. It's an apparent deflection of the direction wind is actually going. Right, and we're going to talk about how that creates what we call prevailing winds in a few minutes. Which direction do our winds prevailingly come from? Southwest. Okay, typically we get southwesterly winds. Okay, we are right at the upper edge of what is called the prevailing westerlies. Okay, that's why occasionally we get winds from other directions. Okay, but we're in the area of the Earth where wind typically comes from the west. Okay, now nature doesn't like imbalance or inequity. So if there's a change in pressure, the Earth's atmosphere will move in order to balance it. If there's a change in temperature, the second law of thermodynamics says the Earth's atmosphere has to move in order to transfer the energy from hot to cold, right? So this is the dynamics of that system, making the atmosphere have to flow, because it's a fluid, to balance these pressures. Sorry, changes in pressure and temperature. All right, so wind transports heat energy, okay, as moisture, okay, influencing the global climate. So heat energy and moisture could be sensible heat, and moisture could be latent heat. Okay, the Earth does not the atmosphere does not transfer liquid water from place to place. That it doesn't have the ability to do that, but it moves water vapor, which can then condense. Okay, how many people have heard of the jet stream before? All right, so the jet stream is this high altitude wind mechanism. Okay, it moves around all the time. Okay, its position is based on high and low pressure areas, and they can change its shape and force it to do different things. When they force the jet stream to move around, the jet stream can bring air masses from different parts of the globe to new areas, and in that way can transfer large amounts of both sensible heat and latent heat, water vapor. Okay, so in this particular diagram here, on this particular day, there was a high pressure system right here, which is an odd place for it to be because normally this is an area of low pressure. Okay, so there probably would have been an area of low pressure right here. So the jet stream was being forced around this high pressure area. Okay, and there was a big air mass here that was full of cold air because obviously that's over the Arctic Ocean. Okay, so the jet stream was pulling this warm, dry air up and over and making it interact with this chilly air here. And when it got wrapped around this high pressure area, the jet stream started pulling the cold air from the north down into this area. So we had a place that was warm and dry because it was bringing all this air in, and then the jet stream started pulling air from here, making this area cold. Okay, and then down in here, it became unsettled. Right now, if you look through the part of the United States that is unsettled here, what do we call that part of the United States? Well, it's part of the Midwest, but it has kind of a more common name. Tornado Alley. Yeah. Okay. This is Tornado Alley right here. So what you have is that there's this chilly air that's being pulled southward by the jet stream, and then the jet stream got forced out over the ocean where it pulled in a whole bunch of warm, wet air and sent it right back to where it had previously pulled all this cold air. Now, what happens when you get warm, moist air meeting cold, dry air? Bad stuff. Okay? You get an interaction of complete opposites that produces unsettled weather that makes thunderstorms, tornadoes, hail, all that kind of stuff. Okay? So that was what was kind of producing that. Everyone follow? Okay? Now, if you look along through here, okay, this whole area here, actually even a little bit further south than that, okay, to about here is what we call the area of the westerlies, okay, where the prevailing winds are from the west, which is why if you've ever watched the tracking of a hurricane, okay, the hurricanes form kind of down in here, and then they move eastward, and then they always seem to, as they meet the coast of the United States, start to track along the coast like this and move back out to sea. Because down below this line, the winds are from the east. So it pushes the hurricane towards the shore. And then when it gets close to the shore and kind of crosses this line, the prevailing westerlies keep it from making too much landfall and going too far in. Okay? They redirect it, they turn it and force it back out to sea. Of course, once it gets over land, it loses all of its energy because it needed the ocean to build it. Okay? And so it kind of slows down and deteriorates and then heads back out and dies. Okay? Everyone follow on that? Okay? That's why you see that typical tracking pattern for a hurricane. All right, so what's the jet stream? All right, major wind mechanism, and it's at a high altitude. Okay, its role, okay, to move large air masses and latent heat. Okay, meteorologists are always watching the jet stream. The position of the jet stream is what determines what our weather is going to be like. Okay, where it is going to determine where air is going to move from. Okay, when we had the polar vortex thing going on, okay, the jet stream actually looked a little bit like this, except it didn't have this big wow in it. It was more kind of down in this area, and that was pulling, okay, air down in this direction from the polar vortex, actually making it do this. Okay, it was actually circulating the other way and coming this way, right? Because the jet stream was so low during that time. Okay, the jet stream has since moved up a little bit, and that's of course why we're getting all this wicked wind right now, is because the jet stream is actually running right over top of us right now and blowing along that way. We're not feeling the jet stream here, we're just feeling its effect that is drawing air from another place and making it move quickly. Everyone follow on that? Okay, now it's called the jet stream because what wants to use it? Jets, yeah. If you're a pilot and you're flying from west to east, you want to catch the jet stream. The jet stream never goes the other way in the northern hemisphere. Okay, it always generally goes from west to east. So if you're flying from west to east, you want to try and catch it at least for part of your flight if you can. If you're going the other way, you want to avoid it. If you're crossing it, you want to avoid it. How many people have been on a very turbulent aircraft ride? If you were on a turbulent aircraft ride, you were crossing the jet stream, or you were flying the opposite way it was going and you were too close to it. So what do pilots do when they start to hit turbulence? They change altitude, right? They go a little bit lower down, they're out of the jet stream. They go a little higher up, they're out of the jet stream. Okay, they kind of have to find that delicate balance. Okay, but if they're flying from west to east, they can save a lot of fuel by getting in the jet stream and letting it blow them in the right direction. Okay? And sometimes you even arrive at your destination a little bit early because they travel a little faster than they had expected. If you're going the other way, it slows you down. You have to avoid it. You have to travel out of the normal flight path, okay, in order to avoid this wind. All right, did everybody write that down? Okay. All right, global wind patterns are areas of prevailing winds, okay? This is what the Earth essentially looks like in terms of the atmospheric movement that is generally occurring. So near the equator is where the bulk of the solar energy is being absorbed and striking the Earth's surface. So near the equator, hot air is rising. So that's what we see right here. Okay? Hot air rises and is pushed upwards. Okay? And other air moves in to replace it. So that air is coming from higher latitudes, but still not really far north. So we're still talking like, in Mexico, Central America, maybe the very southern United States. These are still warm areas. So we've got warm air, just not quite as warm as this air, moving back down, okay? And then wind moving this way. So this is a convection current, which is also known as a Hadley cell, okay? That's set up here. When that air that's risen and been forced northwards, okay, gets to about the horse latitudes, which is about 23.5, 30 degrees, somewhere in there, okay? Then it starts to duck underneath and move northwards. Now remember, this air came from the equator. So it's warm and it's moving northwards along the surface. Okay, so we've got areas where wind is doing this, okay, or air is doing this, where it's moving this way, and then other areas where it's going the opposite direction. Here, wind is moving from north to south. Here, it's moving from south to north. This is where we live. Okay, we're right here, right at the very northern edge of this area. Near the pole, it's back to what happens at the equator. Okay, which is this other circulation like this. Okay, air is moving from the pole back down here because this air is hot and moves up above it. Now, because the Earth is rotating underneath its atmosphere, okay, and it's rotating this way, air that's moving downwards or from north to south gets deflected because the Earth moves under it while it's doing that. So it doesn't appear to come straight from the north, it appears to come from the northeast. It gets deflected a little bit this way. Everybody follow me there? Okay. At our latitude, because it's moving the other way, it gets deflected opposite. It gets deflected to the west or to the east. Okay, and we get these southwesterly winds. Okay, we sit right on the border of that. Okay, if you're further up, then you typically get northeast winds, which means the wind's always coming from the pole, always bringing you sucky weather. Okay, it's going to be like cold and dry and nasty. Everybody follow there? Basically, at our latitude, cold air stays aloft where it's cold, and this hotter air gets kind of wedged under it. Okay, and it's just because of the polar vortex up here at the top. Okay, that's causing air to try to move south. Okay, the hot air can actually wedge underneath that like a door jamb. Okay, and just get underneath, so it always moves that way. Okay, all right. Now this deflection of the winds is something called the Coriolis effect. Okay, on Earth we get 3 bands of this movement. Okay, and this deflection. If Earth was larger, we'd have more bands. Okay, but Earth is small, so we only get 3. Okay, so we get a convection current here, a convection current here, and then a convection current up near the poles as well. Okay, but that convection current near the poles, because the Earth doesn't rotate as much up here, okay, tends to spiral more than it does up and down. Now, at the equator, these easterly winds, okay, are called the trade winds, right? So these winds here are called trade winds, okay, because they used to bring trade from the old world to the new world. So if you wanted to go to the Americas back in the era of sailing ships, you actually had to travel south to catch the trade winds, which would blow you to the west. And then when you got to here, okay, you could redirect, get up onto the coast, kind of like tracking a hurricane. You follow the same path as a hurricane does. Okay, you get up to the coast, and then to go back, you catch the westerlies. So it was this big cycle that had to be used in order to get from Europe to the Americas. And that was kind of the path that they had to follow. You can't just put up your sail in an easterly wind and hope to go the other way, right? It just doesn't work. All right. Questions on that? So this is all caused by inequity in the amount of solar radiation that happens, right? Lots of solar radiation hits here, so our air is always moving up and away. Whereas at the poles, the cold air is being pulled down because the heat is trying to move in general towards the colder area. Okay, everyone all right with that idea? All right. So on its way, okay, on its way to the poles, or on its way down, okay, in this case, because the air near the surface is actually moving southward, we get that deflection, okay, like we said before, and we're going to get our trade winds here, okay, our westerlies, and then our polar easterlies up here near the pole, right? So you get, again, these Hadley cells. This is just a convection current. Hot air rises, cool air descends, okay, hot air rises, okay, cool air descends, this cool air kind of wedges in underneath, okay, at this latitude here. All right, you can see this even better on a planet whose atmosphere isn't clear. Okay? On Earth, it's hard to see this pattern because our atmosphere is transparent. Okay, but on Jupiter, where the atmosphere is made of hydrogen and helium, you can actually see the bands, okay, of these winds. Right, so these are the trade winds here at the equator, and then there's different bands of color the further up you go. Okay? And actually, if you look at the poles on Jupiter and Saturn, you can actually see the polar vortex at each pole. There's almost like an eye of a hurricane kind of a formation. On Saturn, it actually looks like a hexagon. Okay? But that's what's happening at those poles. And you can actually see the air moving away, okay, from the poles. Everybody with me there? I'm going to show you a video here because you can actually see the movement on Jupiter of the winds going opposite directions, because you can see the gases moving past each other. All right, so you could see there, guys, that the winds, I mean, you could see them on Jupiter just because they were different colors, right? And you could see the counter movements there. And a lot of that has to do with not so much that Jupiter gets lots of sunlight, because it doesn't. It's a lot further away than Earth is, but because it spins so fast, okay? It's way bigger than Earth, but spins around in 10 hours, right? That can generate incredible wind speeds.
So what does Jupiter actually?
Nobody knows. There's probably a small, dense core of something near the center, but no one's really sure yet, right? How do you get there? You take a spacecraft. I'd like to be more specific, but I don't really have time. Yeah. All right. Now, the Coriolis effect. Okay, the Coriolis effect is what happens to an object trying to move in a straight path on a curving or rolling surface. All right, so what we have with the Earth, okay, is that the Earth is spinning this way. So you can see the red line down here at the equator, okay, indicating that the Earth is spinning this way. If the Earth was like a perfect ball, and I put a ball on top of the Earth and tried to roll it to the equator, it wouldn't end up directly underneath. Okay, so if I started it rolling, this is where it should go. But because the Earth rotates under it while it's rolling, it ends up over here. Well, actually there, but you get the idea, okay? The target is moving. This is where I wanted to go, but it ended up over there, okay? I got deflected. So if I have a wind that's trying to move from north to south and the Earth spins underneath it, the wind gets deflected like this. And instead of coming straight from the north, it comes from the northeast. At our latitudes, okay, the wind is trying to move straight north, but the Earth is rotating with it and pushing it this direction. Okay, and so it gets deflected the other way, and we get westerly winds. And then at the equator, again, where air at the surface is trying to move from north to south, okay, it gets deflected this way. And because near the pole, it's all moving away, you get this vortex-looking thing at the pole. Partially, yes, and partially it's because of the ocean current that goes by, right? The North Atlantic current is kind of warm, but it's further out. Okay, the Labrador current goes right along here, and it's really cold. Okay, so that's the Coriolis effect. We definitely need to know that one. It's the deflection of any object from a straight path by the rotation of the Earth. All right, Tiana, can I get you to turn that light back on? All right. What is the effect of unequal distribution of thermal energy on Earth? It makes convection currents, exactly. Okay, it's the second law of thermodynamics. We have wind because of the second law of thermodynamics. Okay, it says energy has to flow from hot to cold. It does that by conduction, convection, and radiation in the Earth's atmosphere by convection, which is wind. Okay, Coriolis effect influences the direction of winds in the northern hemisphere. Well, if we're between 30 degrees north and the equator, the direction of the winds is from the northeast. Okay, we get the trade winds, those easterlies. Okay, if we're between 30 and 60 degrees, then we have the westerlies. And then above 60 up to 90, okay, we get the polar easterlies. That's spinning underneath it. That's right. All right, and what are the trade winds?
Oh, they're at the equator. That's because of the Coriolis effect.
Okay, they're at the equator because of the Coriolis effect. They are from what direction? From the east. So they are easterly winds. Winds are always named for the direction they originate in. Okay, we have westerlies because they come from the west and blow to the east. Okay, and the jet stream. High altitude wind mechanism. What is it moving? Large air masses. Latent heat, right. Okay.